light, and then it should.
That's great. A lot of great.
Yeah.
About time. You ready to go?
I'm ready.
All right. So we're pleased to start another series. Matt Headrick from Brandeis is going to be telling us about entanglement in field theory and holography. And before he starts, I just want to mention you've been here 2 weeks by now, and you're probably starting to learn that, yes, there are great lecturers up here, and you're learning a lot from them, but you're also learning a lot from each other. And you should sort of take a look around, and these people around you are going to be your colleagues for the next N years, where N will go to infinity. And so Matt and I were at TASI 99 together. And I'm always glad to see someone from that class come in and speak to you. And our class has gone on to sort of, be people all over the field, all over the world. And that's going to be the same for all of you. So just something to bear in mind.
No pressure. No pressure.
No pressure at all. So here's Matt.
All right. Thanks, Oliver. Yeah, I was just going to mention that they gave me a T-shirt when I was a student here. I hope they're giving you guys T-shirts. And I guess it was a good quality T-shirt. My wife made me throw it out about 2 months ago, actually, and wearing it since then. Yeah, so you can really hold on to it. I'd like to start by thanking the organizers for inviting me. It's really an honor and a pleasure to come here and talk to this crowd. I hope to get to meet some of you over the next week. I'll be here until Friday. Thinking back on my own experience in TASI, I learned a ton from both the lecturers and the other students. I also remember it being just a huge volume of stuff. And so thinking about that, I kind of decided to try to take it a little easy on you guys. So that was a conscious decision. I know there are some people in the audience who are pretty expert in this area, and so I hope they won't be too disappointed. I mean, hopefully they'll learn a thing or two nonetheless from my lectures, but it's not really aimed at them. And so that means what I was tasked to. I mean, I just am following orders here. Igor told me, please give a series of 5 lectures on entanglement in field theory and holography. I said, yes, sir. And that's a huge area, of course. And I could talk about it for a lot more than 5 lectures. So there's a lot that I won't cover, especially given the decision to go at a fairly slow pace. So let me just start with some kind of general blah, blah, blah intro before we get to the actual equations and stuff. I mean, so the first word here, entanglement. So this is one of the phenomena that sharply distinguishes quantum mechanics from classical mechanics. It's also ubiquitous in quantum mechanics, as we'll discuss. And usually, so when we talk about entanglement, the basic thing that we're doing is we have some system, and we've divided it into 2 parts, and we're asking how entangled are they. Okay, and it turns out that this question, just taking some system, dividing it into 2 parts, and asking how entangled are they, is very fruitful in a large number of areas of physics. For example, in condensed matter theory, in high energy theory, and in gravity. And it really helps us to understand all kinds of different systems. Now, what's interesting is how long it took people to come to this realization that this simple question is incredibly powerful and useful. So let me just give like a very brief history. And this is going to be one of those sketchy fake histories that physicists tell each other. So, I mean, but I find it kind of interesting because it's a story where it just took a long time for people to think about it. So, you know, the recognition of that there's this phenomenon called entanglement arose very soon after the development of quantum mechanics, and basically in the 30s. So EPR, if you want, sort of pointed to the importance of this phenomenon. And then nobody really knew what to do with it for like 30 years. So people knew that there was this thing called entanglement in quantum mechanics, but they were kind of a little bit afraid of it. And certainly people in the high energy, like the particle physics community, never thought about it, as far as I know. And in particular, it kind of points to the fact that in particle physics, we often think about systems, even field theories, by thinking about quantities like scattering amplitudes, as opposed to actually taking it seriously, taking a field theory seriously as a quantum mechanical system that has a Hilbert space and Hamiltonian evolution and so on, and thinking about it in those terms. And so finally, the idea of thinking about entanglement in the field theory context kind of came in through the back door in a very strange way. So in the 70s, people thinking about black holes, so gravitational physicists like Hawking and Unruh discovered some strange behavior of quantum field theories in curved backgrounds. And then finally, the big breakthrough was in the 80s, when Sorkin was and collaborators were thinking about these things. They were thinking about black holes and black hole entropy and the puzzle of black hole entropy. And they thought about a quantum field on a black hole background, just as Hawking had been doing. And they asked about what entanglement there is between the fields outside and inside the black hole. And they discovered that that entanglement, so there's a quantity which we'll define later. I'll just write it EE. Entanglement entropy obeys an area law. And they suggested that it may have something to do with black hole entropy. And this was a very exciting discovery. It was so exciting that absolutely nobody noticed whatsoever. 10 years later, Srednicki had exactly the same thoughts. But Srednicki came from a particle physics background, and so a few people noticed. So Wilczek, in particular, picked up on it, and collaborators, and started thinking more abstractly about entanglement entropy in field theories. And then people forgot about it for a few years. Nobody really knew what to make of it, or how to think about it. And when it finally came back around, it came back around thanks to the work of people who think of field theories as describing actual, very concrete physical systems made up of atoms, namely condensed matter physicists. So when condensed matter physicists became aware of this work and started thinking about what it means for their many-body systems, they could sort of think about it more concretely than maybe a particle physicist could, or at least that's how it happened. And so this work was picked up in 2003 by two, basically stat-mech or condensed matter people, Calabrese and Cardy. And they discovered a general formula for entanglement entropy in 2D conformal field theories. And then it went viral in the condensed matter community. but the particle physicists, as far as I understand the history, still didn't really know what to make of it. And the next big breakthrough, so in the next few years, the condensed matter and stat mech people were very busy thinking about entanglement entropies, and then there were two big breakthroughs in 2006. And the first was, again, within the condensed matter community, simultaneous papers by Kitaev and Preskill and Levin and Wen, and I'll explain their work. And they discovered something called topological entanglement entropy. And this was like really a killer app for people trying to understand topological field theories. And at the same time, around the same time, Ryu and Takeyanagi discovered holographic entanglement entropy. And of course, you know what happened. This is an incredibly beautiful and powerful statement. And so, of course, what happened is that everybody ignored it for a few years within the string theory community, except for a small group of us, like myself, Igor Klebanov, and a few other people thought it was intriguing. And it basically took another 5 years or so before it really hit the mainstream. And so now it's all over the place. There's tons of papers every day on the archive on it by particle physicists, by high energy string theory people and so on. Yeah.
I was just going to add a perspective to that, which was that we had a stringy TASI in 15, and before that we hadn't had a stringy TASI in 2010. And in 2015, we're talking about entanglement all the time, and Joe Polchinski pointed out, isn't it strange that 5 years ago, in 2010, pretty much no one said the word entanglement in the entire TASI, and then half a decade later, basically everyone.
Yeah. Yeah, now you have to, or you're nobody, basically. Yeah. Well, I mean, we know that our field is very kind of fashion generated, and so that's kind of how things work. They're a little bit more stable, I think, in condensed matter physics, and they've been thinking about this for longer than us. I'm going to try to explain, we'll see how far I get. I mean, certainly I'm going to try to explain the key points. I'm probably not going to explain the connection to black hole physics too much. But one thing, right, so I think this little history already shows that this is an area of great overlap between high energy theory and condensed matter theory. So, I mean, every so often some topic comes along that leads to us working together, like, Wilson, RG flow, and critical phenomena in the 70s, and in the 80s, classification of 2D CFTs. And every so often something comes along that really makes us want to work together, and this is one of those things. And here we also have the third subject, which is quantum information theory. So with the overlap being. Okay, and then the other thing I want to emphasize is that there's still much more we don't understand than that we do understand about, as you'll see, about entanglement in field theories and holography. And are there any questions about that extremely sketchy history? My outline, very briefly. So I want to spend a while laying the foundations, talking about entropy and entanglement in general, some very basic classical and quantum information theory, then apply those ideas to fields, and then understand the connection to gravity via holography. Okay. Okay, so I'm going to start with some stuff that I presume is not entirely unknown to most of you. We're not doing quantum mechanics yet. We have a probability distribution. So PD means probability distribution, and all the probability distributions I'm going to deal with are going to be discrete. Okay, so we have some set of numbers PA that satisfy that are non-negative and add up to 1. So of course we have, so given a probability distribution and given an observable, so by observable I mean a function of A which doesn't depend on the distribution. So it's not secretly something which depends actually on your probability distribution, which I'm going to distinguish from a function of A, a more general function of A, which could be some, like this itself is a function of A. Okay? So given an observable, its expectation value, of course. I'm not sure why sometimes I'm using subscripts and sometimes parentheses, but anyway. And then we define the Shannon entropy. Which is sum of P log P. And this is not the expectation value of an observable. You can write it like this. It is the expectation value of something, but this thing is not an observable because it depends on the PAs. Okay? Okay, so why do we care about this quantity? Well, the point is that it quantifies your ignorance. Okay? It tells you basically how much you don't know. You know, it's like there's some episode of The Simpsons, I'm dating myself, I know, where Bart tells some woman, "Lady, what you don't know could fill a warehouse." And this is like quantifying what you don't know. Like, how big a warehouse do you need for what you don't know? Okay? So in particular, to support that, I guess if there's some line below which I shouldn't write. The people in the back, if I write down here, is that too low? It's yeah, it's a problem. Okay. So in particular, the only way the entropy can be 0 is if your probability distribution is only non-zero, is 1 for some A and 0 for the rest. And in this case, you know that you have definite values for all observables. Whereas the only other possibility is it's positive, it's never negative. And in this case, so let me just write it like this. Okay, now actually there's a lot of other functions that have the same property. Okay, but the entropy, well, the entropy has a whole lot of useful properties that we'll discuss. But let me first give the killer app, which is this beautiful theorem called the Shannon noiseless coding theorem. And the reason I want to present this is not a physics theorem, but it puts us in mind of thinking in terms of information, which I want to do, which is a very useful point of view. So if we have if we want to basically send messages where a message is an element drawn from this probability distribution. It's a value of A that's chosen from this probability distribution. So maybe it's the letters of the alphabet in the probability distribution is their frequency in the English language. And the message is just some text, which has n letters in it, okay? And for the moment, we're going to pretend that they're drawn independently. Of course, if the text is an English language text, that's not true, and we could do something fancier. But let's just pretend that each letter is drawn independently from this distribution. Okay. And the question, how many bits do I need if I want to code this text? And I want to be clever about how I code it. I guess in principle, there are 26 letters in the English language, so I would need 5 bits per letter if I just do something the simplest possible way. But because the frequency is not uniform, I can be much more clever in how I code this text. Okay, and how many bits I actually need that question is answered by this theorem. So it says that the number of bits to code n messages drawn from this probability distribution, okay, in compressed coding equals n times s over log 2. Okay, the log 2 is because we're physicists, and so we work with natural logs. Of course, in computer science, they just work log base 2 to begin with, and they don't have this log 2. So for example, let's say I just had 3 letters in my alphabet, and maybe the distributions were like this. For 1, I have a half, and for 2 and 3, I have a quarter. And then my efficient coding, so then s over log 2, when you calculate it, is 3 halves. So Shannon tells us that I need 3 halves bits per letter on average. So an example of a compressed coding in terms of bits is to use 0 to represent 1, 1 0 to represent 2, and 1 1 to represent 3. So you notice that I used fewer bits for the more likely letter. And so this happens with probability half. So the number of bits per letter here is a half. This happens with probability a quarter, but I needed a 2 bits, so this is also a half. This happens with probability a quarter, but I used 2 bits in my compressed coding, so this is also a half, so the total is 3 halves, as predicted by his theorem. Okay, so this is one of those theorems that, one of those things that we just completely take for granted in our modern life. But like 100 years ago, I don't think people thought about information in this way at all. What this theorem tells us is that information is something that can be quantified in a meaningful, comparable way. So if I have, 2 different sets of messages, I can quantitatively say which one has more information in a canonical way. Okay? And so anytime you talk about that your RAM has so and so many gigabytes or whatever, you're using some units of bytes to quantify information. You're using this theorem. Okay, it's always there in the background. Okay, and the other thing about this theorem that's incredibly powerful is that there are many quantities that you encounter when you start interacting with people who do information theory. You encounter many quantities that are defined in the following way. There's some task you want to perform. There's some resources, and you want to minimize the resources required to perform the task. And they'll define the quantity to be the minimum number of resources required to perform this task. And then they'll go and prove theorems about these quantities. Okay? But you see, there's something different here, which is that this is a quantity that I can just go ahead and calculate. So I know already without having to actually find the compressed coding how many bits I'm going to need. That's the key. I don't actually have to sit down and find the compressed coding and argue that it's the most efficient compressed coding to get the answer. I just do a very simple calculation of the Shannon entropy, and that tells me already how many bits I need. This is actually very, very unusual in information theory to have something like this. Okay? Yeah. It is basically constructive. Yeah. I mean, it's, of course, to do it carefully, you're really in the large, here I have an n, and what I didn't say is this is in the n goes to infinity limit, and so you're doing some asymptotic analysis. Yeah. Okay. So I just wanted to emphasize the kind of the magical qualities associated to this particular quantity. And now let's, now I want to talk about correlations, which means I want to talk about joint systems. So let me see, joint probability distributions. So I have some PAB, then we can define the marginal distribution which is the distribution if you only care about the variable A and you don't care about the variable B. So we have, so of course we have for any observable on A. Did I use this notation? I didn't. Okay. Anyway, so this is an observable on A. It only depends on little a, doesn't depend on little b. You can, if you just know the marginal distribution, you can compute its expectation value. And therefore, we have these different entropies. For example, I'll write it like this. So now I have in mind, so I'll use the capital letters A and B to basically denote the systems of which little a and little b, or the messages of which little a and little b are instances. So this is derived from, just write it. And we have, I'll write it SA and SB. And sometimes these are written, in fact, even in like the high energy theory community, there's no agreed upon notation. They're often written like this. Okay, why do I care about these? So I have these different entropies. So I have the entropy of the full thing, and then the entropy of just these parts. And let me look at an interesting quantity, which is the conditional probability. So what I'm after ultimately is how this PAB distribution links the A and B variables, okay? And to what extent they're correlated, and how much you learn about one if you know the other, and so on, okay? So the conditional probability for some given a B for A is PAB over PB, okay? And so then we can calculate the entropy. So if we now fix the value of little b, we now have this new probability distribution for little a, and we can calculate its entropy, okay? So which you can write out. And now I want to ask the question, well, so this assumes that I fixed a value for little b, but what is the expectation value of that? Okay, in other words, so this tells you how much you still don't know about a if you know b for a particular value. So what's the expectation value? So we can compute the expectation value of this with respect to p little b, and you do like 2 lines of algebra, which actually I recommend doing if you haven't seen this before, and you actually get a surprisingly simple answer. So this is the conditional entropy, which has a name. So this is, what is this quantity? This difference of entropies. And again, this is something, all you have to do is you just use Shannon's formula to compute this and compute this. And what you learn is basically how much you still don't know about A if you know B. Okay? And it's sort of obvious from the definition that this is a positive quantity, a non-negative quantity. Okay? And in particular, because it's the expectation value, because this is non-negative, because this is an entropy and entropies are non-negative, the expectation value of a non-negative quantity is non-negative. So we have this. And in particular, if you are smart enough to know the precise state of the AB system, then you know, based on the fact that this is non-negative, if this is 0, this must be 0. Okay, so this is a ridiculously obvious statement. So if you know the state of the AB system, then you know the state of the B system. Because if you know the state of the AB system, then there's only one value of the little a, little b variables that's non-zero, and therefore there's only one value of the little b variable that's not, for which PB is non-zero. Okay? Okay, so if the full system is in a definite state, the subsystem is in a definite state. Okay? And now from this, maybe I'll... We learned something else. So if you start, you start with some ignorance about the state of A, which is S of A, and you learn something, and after, you start with some ignorance about the state of A. After somebody tells you B, you now know more about the state of A, which means you're less ignorant, which means that this is the amount you learn. So, amount you learn about A from B. So this is S of A plus S of B minus S of AB. So the amount you learn about A from B is the amount that they're correlated. If they're not correlated, you learn nothing about A from learning B. If they're perfectly correlated, then if somebody tells you B, then you know A. And you notice that this turns out to be a symmetric function. So the amount you learn from A about B is the same. And this is called the mutual information. And it gives a canonical way of quantifying the total amount of correlation. And it actually plays a role in communication theory. For example, Shannon's noisy coding theorem, which I'm not going to go through, uses the mutual information. So how much information you can send over a noisy channel. Okay. And again, it's something that you can just calculate without actually knowing anything about the correlations. So you don't actually have to find the correlations. And in particular, there are cases where there can be hidden correlations. So the other way you could try to find correlations between two systems is by computing a correlation function. You have some observable on the A system and an observable on the B system, and you compute this. This is much more sort of familiar from like a field theory or physicsy point of view, right? If this is non-zero, then clearly they're correlated. But the problem with this is that you may get 0. That doesn't tell you they're uncorrelated, because you may have just picked the wrong variables. And in fact, the correlations may be hidden in some way. But if you know enough about the probability distributions to compute this, and you find it's non-zero, you know there's some correlation. And if you find it 0, you know there is no correlation. Okay? So the only way you get 0 is if PAB, no correlation means they factorize. PAB equals PA times PB. And this is the same as saying that for all observables, OA OB equals. And the only other possibility is that it's positive. It's never negative. Okay, so let me give a cartoon. Basically, there's some coding of your AB system that looks as follows. After you're finished ferreting out the structure of the correlations and you understand sort of how they're correlated, you can draw a diagram like this, where each box is going to be a bit. And this is my A system, and each box is a bit. And what this means is that they agree. So a particular state might be coded something like this, and then these bits that are on top of each other have to agree in this particular coding. And the total number here is S of A. Total number here is S of B. The number that overlap is the mutual information. The number here that are independent is the conditional entropy. So the conditional entropy, remember, is what you still don't know about B, even if you know A. So in this coding, if you know A, then you know all of these. Therefore, you know all of these, but you know nothing about these. This is what you still don't know about B, and this is this conditional entropy. So we just organize our bits into these three categories. The ones that are purely in A, the ones that are redundant between A and B, that are shared, and the ones that are purely in B. And for any probability distribution, again, in an asymptotic sense where you're doing n repeated independent messages and so on, you can organize it in this way. Yeah?
Should there be any relationship?
No. I mean, this could be 0 and this could be 100. You can have as many boxes out here as you want, totally independent from the number out here. I mean, except for the obvious fact that the sum of these three, let's see, or what is it? This plus twice this equals S of A plus S of B. I mean, of course, there's the, they're all linear combinations of these three entropies. Yeah. No, I'm not doing quantum mechanics. You can code it, so you can map the little a and little b variables into bit strings such that it looks like this. Again, what I really mean is with n independent copies drawn from the same distribution, then it can be coded in this way. So this is, strictly speaking, this is in an asymptotic sense. Or alternatively, if you just have a very large system to begin with that has a lot of degrees of freedom. Okay, so that's classical information theory in a nutshell. And now, let's move to quantum mechanics. Well, I guess any other questions? Oh, yeah.
So here, for practical information, you don't have the inequality
between the what and the what?
Inequality, for example.
Oh, yeah, you do. I didn't mention it. I'll actually... yeah, there is an inequality relating, that's true, there's an inequality relating these connected correlators with this quantity. I'll say it when we do the quantum case. Yeah, anything that's true quantum mechanically, if you interpret it right, is true classically. Well, any of these properties. Okay, so let's move on to quantum mechanics. Now here there's a catch, so far we've been discussing that there's some message, little a, which is unknown, and then the probability distribution quantifies what we know and don't know about the value of little a. And in quantum mechanics, the line between, so let me not use the language of messages, let me talk about systems. Some physical system, it's in some state, and then there's what we know about the state and what we don't know about the state, right? Or at least that's how we like to think as physicists, that there's the system, and then in another category, another epistemic category, there's what we know and don't know about the system. And the point is, in quantum mechanics, this is completely blurred. There's no good way to separate the state of the system from what we know and don't know about the state of the system. Okay? And so we put them together in this one object, which we just call the state, or density matrix. Rho, which looks like this, rho equals rho dagger. It's Hermitian, it's positive, and it has trace 1. And for any observable, an observable now is a Hermitian operator, the expectation. Okay, and by virtue of these properties, by virtue of this property, we can diagonalize it, and by virtue of these properties, the eigenvalues define a probability distribution. So in its eigenbasis, it looks like a probability distribution. So rho equals sum on A PA. So if we just had one, if there was just in the world one density matrix, then we could just diagonalize it and be done, and then we wouldn't have quantum information theory. We wouldn't need it. Okay, so then one obvious thing to do, since we can at least temporarily think of rho as being a probability distribution, at least with respect to some basis, we might as well go ahead and compute its Shannon entropy of that probability distribution, and that's of course the von Neumann entropy, although historically it was the other way around. Von Neumann defined his entropy in quantum mechanics like 20 years before Shannon. And we can write this in a matrix equation. Okay, and again, we have the fact that if S is 0, then there's just one non-zero PA, which means that rho is a projector. And we call these pure states. So this is, we know, so this is as much as you can possibly know about the state when it's pure, but unlike in the classical case, as we well know from the uncertainty principle, it's not unlike in the classical case where this meant that for all observables we had a definite value. Here we have some observables have a definite value. Meaning definite value means zero variance. And the only other possibility is that it's positive. And we call those mixed states. And in a mixed state, well, it's the same deal. Some observables have definite values. Not all. Not all have indefinite values either. Okay? So there's no, actually, it's not such a sharp distinction anymore. In this case, some observables have a definite value. In this case, some observables have a definite value. Okay? It's not a qualitative distinction. Okay? One of the nice properties of the von Neumann entropy, so this is something that comes up in quantum mechanics but not in classical mechanics, is that we can do basis changes or unitary transformations, and one of the key properties is that the von Neumann entropy is unitarily invariant. Okay, and as you guys know, like if you look at something like a Gibbs state, thermal state, then this is the thermodynamic entropy. Okay, so before we get to entanglement, I want to pause. Actually, are there any questions? I assume this is review for everybody. But I want to talk about a different kind of entropy, which plays a role, an important role in field theories. And this, so at the moment, and I apologize for this, so this is like just a technical tool. Okay, so there's not going to be a huge amount of physics for a little bit. But this is an important tool that people talk about all the time. And these are the so-called Reni entropies. Have you heard the joke that a mathematician is a device for turning coffee into theorems? So that's the other thing this guy Reni is famous for. He made that joke. So actually, he was not. So I'm going to discuss it as if it's something about density matrices. I mean, the dude was just talking about probability distributions. So actually everything is just probability distributions. But in our field, it's applied to density matrices, so I'm just going to use that language, okay? All right, so you have a real parameter. So alpha is a non-negative real number all the way up to infinity. And it's just a different way of measuring mixedness. So it's another quantity which also has this property that it's non-negative and 0 if and only if the probability distribution has support on a single element. Okay? So basically that's going to be the punchline. It's another measure of mixedness. And I'll tell you in a minute why people care about this. Okay, but anyway, here's the definition. Okay, this definition only makes sense when alpha is not 0, 1, or infinity. In those cases, you take the limit. So S0, if you take the limit, what you find is that you get 1. Let me work here. If you take some number to the 0th power, you get 1 unless the number was 0 to begin with. Remember, we're taking the limit alpha goes to 1. Sorry, alpha goes to 0. So if PA is 0, you get 0. So this is the log of the rank of rho, number of non-zero eigenvalues. S1 is S. If you take the limit alpha goes to 1 and use L'Hopital's rule, you get von Neumann entropy. And S infinity is, if you take the infinity power of some number which is between 0 and 1, you get 0. But here we're dividing, after taking the log, we're dividing by alpha. And in the end, the only thing which survives is the largest PA. So this ends up being the log, actually minus the log of the largest eigenvalue. So this tells you about how many non-zero eigenvalues. This tells you about the largest one. This is something in between. So depending on the value of alpha, you're kind of probing different aspects of this probability distribution. Okay. We have, it is a measure of mixedness. So for any alpha, S alpha equals 0 if and only if, let me write it like this, rho is pure. And it's also unitarily invariant. And it has some other nice properties that we'll discuss. But why does anybody care about this? Actually, I don't know why Reni cared about it. I'm sure he proved some great theorems using it. But I'll tell you why physicists care about it. So first of all, if you can compute somehow S alpha, then you know more about the probability distribution than if you can just compute the von Neumann entropy. So in particular, if you know S alpha for all alpha, you can invert that in principle to learn the full probability distribution. Okay? It's basically the moments. I mean, essentially, it contains the information about the moment, all the moments of the probability distribution. Now, you might say, how would you know the S alpha if you didn't know the PAs to begin with? But here's where the cleverness comes in. If I give you a density matrix and I ask you to compute the von Neumann entropy, so we have trace rho log rho. Now you got to compute log rho. Well, how on earth do you compute log rho? Well, you basically have to diagonalize rho. Okay? So the problem of computing S looks like it's as hard as the problem of diagonalizing rho. And maybe rho is defined as a state of some field theory or something. I mean, I don't know. You know. But if you know rho in any kind of explicit form, you should be able to square it, hopefully, and cube it. So the operation of squaring or cubing an operator, okay, hopefully, I'm going to assume that we can carry that. In fact, we're going to see a lot of examples where we actually do that by manipulating path integrals, okay? So for alpha equals 2 and 3, positive integers, you have a good chance of being able to directly compute this without diagonalizing rho. That's the point. You can compute S alpha for alpha equals 2, 3, 4, and so on without diagonalizing rho. Now, that doesn't tell you S, but under some conditions, S alpha is an analytic function of alpha, and under some more conditions, it has a unique analytic continuation given the data that we just specified, namely the value of S alpha on the integers greater than 1. And then read off. If you succeed in doing that, you can read off the entropy. So the most common use of Reni entropies in our field is as a mechanism for calculating von Neumann entropies by this trick. Doesn't always work, but we'll see some examples. Okay? And let me give an example of just something you can do as an exercise, maybe something slightly. So in a way, the word entropy is a little, well, it's a measure of mixedness, but you'll see that it doesn't really jibe with our thermodynamic notions of entropy in the following sense. So everyone's favorite mixed state is a Gibbs state for some system with a Hamiltonian, so rho 1 over z e to the minus beta h. And then you go ahead and you calculate, so this thing, you can take the alpha power of it, so you get e to the minus alpha beta h, z to the alpha, and then by the time you're done taking logs and whatever, this is what you get. It's actually a difference of free energies. Oops. So this is the free energy at 1 over t. So this is the free energy at 1 over t equals alpha beta. So for a physicist, this is kind of what the Reni entropy is. It also has some other properties as a function of alpha. For example, you can show that it's decreasing and convex. These are useful to know when attempting to do this kind of extrapolation. Especially sometimes you can do the extrapolation actually numerically. Like you would compute. Okay, so what happens often is that you are smart enough to do this first step, and you can compute S alpha analytically in closed form for any specific value of alpha, but then you get stuck on this step. But this step you can try to put on a computer, do a fit and a numerical extrapolation. Yeah.
So for the first time, you need the red in all the.
Well, of its spectrum. Of course, it doesn't know anything about the eigenvectors. Well, this probably depends on some assumptions that I don't actually know off the top of my head. Under what conditions knowing all of the moments of a distribution tells you the distribution? I mean, if you know all of the S alpha, then you know all the moments. But then I think in practice, that's enough to know. Like in cases I know where people have actually sat down and tried to invert, given the Renis, and find the probability distribution, there's no question about uniqueness or whatever. I mean, that's, yeah. Yeah.
Are there examples where this fails, like where you just have the integers? Are there examples like that?
They don't seem to come up in practice. So, so indeed, it's true. You could worry about this step. The point here is that, like a counterexample to there being a unique analytic continuation is just the function sine alpha over pi, which vanishes on all the integers, but doesn't vanish in general. So you could add that and get a different answer. It wouldn't actually give you a different answer here in that particular case, but it wouldn't give you a unique analytic continuation. But there's something called Carlson's theorem, which tells you if you know enough about the behavior in the complex plane at infinity of your function, in particular that it doesn't grow like e to the alpha over pi up and down the imaginary axis, then it's unique. And so people basically use that theorem to rule out things like that. But in practice, it doesn't seem to be too much of an issue. Like you just fit to some reasonable looking analytic function and that seems to fix it. In practice, people are not too careful about that issue. I've never seen a paper where somebody says, somebody else's analytic continuation was wrong. Here's my analytic continuation, given the same data. I mean, in principle, it could happen. Any other questions? Okay, but I want to tell a cautionary tale about Reni entropies, because they do come up a lot. And I want to answer the following question, which might have occurred to you. How come when I was in high school learning thermodynamics, we didn't learn about Reni entropies? Why did we only learn about entropies? And the answer is very important, that the Reni entropies are not actually thermodynamic quantities. By a thermodynamic quantity, I mean that when you do thermodynamics, like you have some system and you're working in the thermodynamic limit, there are some quantities which don't care about the details of how you took the thermodynamic limit, and there are others which do. So the quantities which don't care, for example, which don't care which ensemble you used. Did you work in the canonical ensemble or did you work in the microcanonical ensemble? And we all know that it's very important in thermodynamics that you don't have to care too much about those details. You have to care if you're interested in more fine-grained information like fluctuations. If you're interested in how the energy fluctuates, well, it matters a lot whether you're in the canonical or the microcanonical ensemble. But if you're just doing straight-up 19th century thermodynamics and you're working with, you know, enthalpy, entropy, free energy, and stuff like that, and you have like a reasonably well-behaved system that has whatever phase transitions it has in the thermodynamic limit, the whole point is you don't have to care about which ensemble you're working in. And that's true of the von Neumann entropy. And it's not true of the Reni entropy. So the Reni entropies for alpha not equal to 1 are very sensitive to fluctuations. So, I mean, so I already computed for you the, did I just erase it? No, where'd it go? I computed for you the Reni entropies in the canonical ensemble. And we can do it in the microcanonical ensemble even easier. So the microcanonical ensemble is that you have 1 over n the sum over all states with energy in some range. So I have some band of energies between E and E plus delta E, and then as long as my energy eigenstate is in that band, it gets included. This is the number of them. This is the microcanonical. Notice that the distribution is flat. Everybody has the same coefficient. And when you plug that into that formula, if your rho is proportional to a projector, in other words, it has just constant eigenvalues, constant non-zero eigenvalues, then all the Renis are actually the same. So if PA doesn't depend on A, then the sum on A of this is just P to the alpha minus 1. And then you take the log, it cancels, and you just get the log of n. If you calculate Renis and you get an alpha-independent answer, then you know that your density matrix is proportional to a projector. Okay? And that's, of course, true for the microcanonical ensemble. And so we get different answers for the Renis. In the limit alpha goes to 1, this goes over to just the regular von Neumann entropy, of course. And this also does up to small fluctuations. Okay? So if we have some parameter, I shouldn't have called this, well, yeah, let me call this little n. So if we have some parameter which is the number of degrees of freedom that we're taking to infinity, and we organize things in powers of 1 over n, then at leading order, so then our entropies will be proportional to n, and that leading order thing will be the same whether we're doing microcanonical or canonical for the von Neumann entropy. But already at leading order in n, the Renis will differ. Okay? Okay, and to understand this, to put it maybe a little more mathematically, when we're doing the thermodynamic limit, essentially what we're doing is a saddle point approximation. So we have some parameter n, which is kind of multiplying all of our entropies and free energies and so on. And when we do the various Laplace transforms involved in statistical mechanics, then those just become Legendre transforms because we're working in the saddle point approximation. But notice what happened to our rho. So if I take rho to the alpha, so if I start, let's say, in the canonical ensemble, and I compute rho to the alpha, I've effectively changed the temperature. So I will pick up a different saddle point when I now go to do my saddle point approximation. I've effectively changed the temperature. Okay? So no longer am I learning about the system in the state it's in. I'm learning about what the system looks like at a different temperature when I calculate a Reni. Okay? So I've actually changed the state from a thermodynamic point of view to a different state. Okay? This is going to come back to haunt us when we talk about Reni entropies in the holographic context, because holography is, again, about a large n limit, a thermodynamic limit of a field theory. That's right. So actually, we mix up, and that's why it's actually, the Reni entropy actually includes information about what the system looks like at two different temperatures. It's a very weird, it's not a nice quantity, really. Was that your question? Yeah. So we expect S alpha, first of all, to have phase transitions first of all, as a function of alpha, because you're effectively changing the temperature, and to have regular phase transitions, let's say whatever thermodynamic phase transitions it had for fixed alpha, at different temperatures, at different values of the temperature and chemical potentials and other external parameters than the system itself. So if you calculate like the Reni for alpha equals 2, you'll find that, and then you start dialing your temperature and so on, you'll find that S2 undergoes a phase transition at twice the temperature that the actual system, the system at some temperature is perfectly analytic, but meanwhile S2 is showing some non-analyticity. Okay? Okay. Yes, question. Well, I mean, yeah, so phase transitions in general are related to Stokes phenomena. And here it's just that now we've monkeyed with the function. And so the Stokes phenomenon happens, it's somewhere else from where it does in the original functions. I mean, it's sort of, if I have some function that has Stokes phenomena, now I take the alpha power of it, alpha is 2 or whatever, of course, that moves the walls around, whatever. I mean, that, that's mathematically trivial, but it's sort of, I don't know, yeah, it's taken a while for this to permeate to the physics consciousness. Yes?
Yeah, so how does the phase transition
Yeah, so exactly. You have to be very careful, and if there is a phase transition, you have to make sure. I mean, in principle, it can ruin this whole program because the function is not analytic. Now, if you know where the non-analyticities are, and really all you need to know is what the function looks like in the vicinity of alpha equals 1. But of course, if there's a phase transition between 1 and 2, you can know everything about what it looks like at 2, 3, and so on, and you just haven't learned what it is at 1. Mostly people just ignore this, and when we get to holography, we're going to ignore it. I mean, I'll flag it, but it's really not well understood how to treat it properly. In practice, when you're actually sitting down and computing in some given system. I'm not going to go on to the next section, so are there any more questions? Okay, time for lunch.